All right, so thank you everyone for attending this webinar. Today's webinar is on designing RF traps that we would use to control excessive emissions from microwave cavities. This is an important issue for EMI EMC applications and for a number of other reasons that we will cover shortly. So the goal today is to keep this webinar to 30 minutes. And it will be presented by myself, Ammar Kuki, and part of the presentation will be given by our senior application engineer, Alex Post. And so today's agenda is we'll give you a short introduction where and how you need to worry about EMI issues, EMC issues. And we will show you how you can address such issues using our software package. And we will hopefully have some time for Q&A. By the way, if there are any questions, feel free to type them into the chat box and we'll try to address them as we go along. Right, so let's get started with the introduction. So the issue of EMI and EMC arises whenever you have undesired microwave leakage. So microwave leakage can arise from many reasons. Typically, whenever you're trying to seal cavities, let's say like your microwave oven or similar structures, then if you don't have an electromagnetically tight structure, then you'll have fields leaking. And then if you have other devices in proximity, then you can have interference issues. And so on. And so therefore, for those reasons, you need to carry out EMI and EMC testing to validate your product. So, so in anticipation of testing, you could do some simulation, you could do some design and validate your design to make sure that when you go and get tested and validated and to get your certification, you're not sent back. These regulations and EMI EMC also arise from regulations imposed by regulatory bodies like the FCC, whereby to manage spectrum and to limit the leakage of microwave energy, there are strict rules how much energy can be radiated at certain points and so on. So there are some spectrum issues, but there are also increasingly important health issues. We know that microwaves can heat. We use them at home to cook stuff. So the FDA has limits in terms of how much exposure people can be subjected to RF and microwave energy. And those also are part of an overall health concern for microwave usage. Okay, so for all these reasons and even beyond, you can be interested in doing some EM simulations and figuring out what your fields are doing and if some adjustments to your designs are required and so on. So the solution we offer is a duo, the SolidWorks HFWorks duo. So the SolidWorks HFWorks duo is essentially a combination of what we believe is a best-in-class solution in terms of CAD capabilities. That is the CAD environment in which you capture your designs and build your geometry models and so on. It's all inside SolidWorks. And SolidWorks is recognized by the engineering community as a leading 3D package. It offers quite a bit of features in terms of making designs, making multiple configurations, playing with materials, and so on. And on top of that, HFWorks is really a seamlessly embedded field solver, which will do 3M field simulation. And it will do so for high frequency, meaning that we're looking at structures that would be on the order of wavelength or a substantial portion of a wavelength. So HFWorks is obviously, as you'll see shortly, is fully embedded inside SolidWorks. It is a gold certified product, which means that the way it's hooked into SolidWorks must respect stringent rules in terms of user interface and so on. So you will not feel like you're actually using a separate product. it will really feel like you're using SolidWorks. And in addition to doing electromagnetics, you can also do electrothermal simulation, and in the near future, we'll also be able to do stress calculations and deformation due to microwave energy. So these are all features that HFWorks brings to the user. And of course, it leverages everything that SolidWorks has to offer the designer, namely the ability to work with multiple configurations and to parameterize designs and so on. And I hope that the brief demo will give you a good idea about and a good feel for this kind of integration and the features that come with it. So when we do an RF trap, we could be interested in looking at a number of different things, you know, in terms of results. Today, we're going to use an S-parameter simulation and to see what the response of our structure is going to be. And so the model that we'll focus on today is essentially the idea of reducing EMI emissions really relies on this basic concept of using serrated structures with lambda/4 choke. So if you look at the microwave door on the upper right corner, that real picture, then you can see that there are some of these structures in there, and their role is obviously to reduce emissions, and the results will show you, will convince you of the efficiency, and will allow you to actually quantify the efficiency of your choke. The example we'll do is also today we'll focus on the ISM band, the 2.45 gigahertz, and we'll be using aluminum, or probably today we're going to use also a copper structure with a size of about 17 by 6 by 2.3 inches. Okay, so this is the what we want to do today. I think at this stage we'll probably turn things over to Alex, and if any of you have questions, don't forget to use the chat box and to write down your questions so we can address them. So with that, I'm going to turn things over to Alex. Okay, so I'm going to make Alex the presenter, and off you go. Alex? Okay.
Hello. Good afternoon, ladies and gentlemen. Thank you very much, Dr. Amar. So, as my colleague presented to you in the introduction, we're going to discuss how to design a serrated structure using HFWorks, which is an embedded application inside SolidWorks. So imagine that you have a microwave oven. So it can be a kitchen microwave oven, or it can be any microwave furnace structure, an industrial one, okay? The moment that you're going to close the door of the microwave, this door of the microwave, there are going to be some inevitable openings all around the door, okay, this area, that we do not have any control over them. So at least a millimeter, a couple of millimeters of opening is going to be there. And we know that longitudinal slits are very easy for microwave to escape from. So this is going to be a huge issue, and we're going to have like a problem with microwave leakage. So the way that we stop it is to use the quarter wavelength choke. And this transparent structure is resembling our door. So all microwave ovens, if you open the door up, you will see that they do have a kind of finger structure like this inside them. Why? Let's go look at this more closely. You will see that there is an opening. Look, there is an opening here. Okay, there is a 2 millimeter opening between the door and the cavity, actually, which is where the microwave tends to leak from. So applying a structure like this is going to work as an RF trap that doesn't allow any microwave to go away. So let's see how do we do it. We have this model in SolidWorks. So we come to our software, HFWorks. So there is a tab here, HFWorks. So we'll just define a study. In this case, our study is a S-parameter study. We can, in the software, we can have S-parameter study, resonance study, or antennas study. So here, we're going to choose an S-parameter study. And we have the option to do a fast sweep or to do a discrete sweep. And also, we have the option to use our multi-core solver or direct solver. We define our frequency range. For example, we say for this one, our frequency is 2.45, that's the ISM band. But let's say we're going to monitor the leakage from 1 gigahertz to 5 gigahertz. And how many number of frequencies in between we can decide. Let's say I'm going to check, let's say 41 frequency points in between. It means with the frequency steps of 0.1 gigahertz. So I will simply define my study. After I define my study, in the pre-processing, I have 3 main steps. First, I have to define my material. So in this model, I have 3 main bodies. So this one, which is my tunnel or my microwave cavity, inside that, I have air. Inside the microwave cavity, there is air. So my material here, I can simply come and either I can choose from my favorite material, or no, I can apply material. So we have a big material library here. So we can choose the material from here. I apply to the other RF trap. It's going to be copper here. And also the door, it can be either plastic or it can be, it depends. So in this case, we can do it plastic, for example. So next step is to define our boundary conditions, which is a very important step. Here, we imagine that here is going to be our port where our microwave is coming in, because it's going to be our microwave cavity. But I choose PEC, perfect electric conductor, to be my boundary conditions for the body of my microwave cavity, right? And also, the boundaries of the door are also perfect electric conductor. Sorry, I was reading the question of M. Hirsch. Is asking what is the RF trap? Like by RF trap, we mean a structure that can stop the microwave leakage. So basically, we trap the microwave. So I'll answer all other questions at the end of the webinar. So the third step after defining our boundary condition, again, for our boundary conditions also, we do have a complete library of whatever boundary condition that we have. It's either perfect electric conductor or no. It can be a lossy conductor. It can be a resistive surface. It can be a signal. It can be a lumped element. It can be a magnetic conductor. So we can use all kind of possible boundary conditions on our surfaces. Then we need to mesh. We need to create a mesh for our model. So in this case, like, let me show you the mesh. Look, I have meshed it before, but we have the option of having a coarse mesh or a fine mesh. So the antenna designer or the RF specialist who is doing this, depending on the accuracy that he needs, he can define the size of the mesh, and he can customize its accuracy and to compromise. Okay, I don't need a very heavy study, but I would like to have a coarse coarse mesh. Or no, I don't mind to have a heavy study. I need very, very accurate result. I can make a fine mesh. But sometimes you say, okay, no, I don't need a fine mesh everywhere, but I need it, for example, at the certain edge. So what we have is we have the mesh control option. So on the mesh control, you apply mesh control. You say, okay, I want to apply a certain size of mesh on a certain body, or no, on a certain surface, or only on a certain surface, or no, at least only on a certain edge. You can apply a mesh control to make your mesh finer at certain edges. When you have sharp edges, you want to avoid singularities, you can actually use this mesh control option, which is a very neat option because you're not going to make your problem so huge, and at the same time, you're going to increase the accuracy of your results. So after you mention, you see actually right here when you want to mesh your structure, it gives you the option run analysis after meshing. It means that this is the last step. So you can run your analysis after you meshed, or you have the option to mesh and run right here. So when you run the study, you're gonna, after like a few minutes, you're gonna have your results right here. So first of all, let's take a look at the electric field here. Let's take a look. You can create a 3D fringe plot, either with clipping or without clipping, or a vector plot. Let's do a fringe plot without any clipping. Okay. So if you look at the electric field, you see that the electric field is traveling in the multimode cavity, in the microwave cavity, but when it gets to this point where our structure is, it looks like it's trapped. It cannot find its way out. You see, look at this side, outside the door, no electric field. So we have trapped the microwave here using this serrated structure. And sometimes we say, okay, I need to see the movement of the electric field. Say, okay, no problem. You can animate the electric field versus phase, okay? So you can show the movement of the electric, you see? You can simply show the movement of the electric field, but there's no way that it goes away from the trap. Or we say, okay, I want to see more details from a certain section. So I will simply come here and I can do clipping. I do a section clipping. So my section clipping, look, I can do it from this cross section, from this cross section, or from this cross section. So I think this cross section is more interesting to look. So let's look at the electric field from this cross section, okay? So let's keep it like this. You might want to animate it this way. So I just animate it to see the movement of the electric field. I don't know if you can see it on your screens or not. So then you can look at your magnetic field. Of course, you can, if you want to look at the magnetic field, so it's also available to you. You can do all those features like section clipping, or you can also do ISO clipping. So it will show you the field only on ISO surfaces, and you can basically define your ISO surface here, at which surface you would like to see the field. You can also see your results at the port field. So then you can do your 2D plots, of course, which is for microwave engineers, it's the most important part. They want to see their S11. So you go to your plot, you define you want your S11, add this. So you get your result for S11, for example. Okay, or you want to see your S12, the same thing. Just add. That's it. You get your S12 results over here, and you can go over the frequency range to see what is the value at any certain frequency point, or you can have access to the result table, and you can export it to your Excel sheet or anything at any frequency. My main frequency is 2.45, so you can see your generalized S matrix, your renormalized S matrix, impedance matrix, admittance matrix, port results, and your VSWR right here. Also, if you want to look at the Smith chart, you can plot your Smith chart. And there is also a very neat feature, which is the report. So you can define a report here. You can generate a report. You can either generate a report in Microsoft Word or in HTML. And it can have cover page, it can have your own logo, it can have your study properties. Like, look, you will choose what you want it to have. Even, for example, if you want the model view, you will choose which model view. You want the current view, you want the front view, you want the back view. And then you can ask the software to generate it in Word or generate it in HTML. Let's do it in Word, for example. You see, it will. Okay. So see that the Word will open inside the SolidWorks for you. The whole report is right there. So if you wanted to share your results with someone else, you will just share your Word file. And so I would save it all. Okay. So I'm ready to take the questions. So let me see. Okay, I'm trying to take a look at the question. So I think I answered the question regarding the RF trap. Then the energy AVI, the energy generated within the cavity is multipolarized. How does trap handles the different polarization? Yes, you're right, because this is a multi-mode cavity, like the microwave cavities are multi-mode cavities. We have only modeled one of the modes over here, but these RF chokes, they work because, you know, it's based on the quarter wavelength, right? Since we know the operating frequency, which is 2.45 gigahertz, the structure is going to handle all the modes in that frequency. So this is going to take care of that. And also because, you know, when you do EMI EMC testing at 1 meter, 3 meter, 5 meters in those approved labs, you care about the operating frequency, and you care about also the harmonics too. So this one is a trap like this is going to take care of both.
Yeah,
so
Alex, yeah.
Yes.
Can I interject and add something to this question about
Yes.
multi-mode? So the concept of the modes depend, which modes get excited depend on the excitation, how you feed your structure. Okay, so let's say because we showed you today how to do this with this parameter, you could as easily do this with antenna simulation, where let's say you wanted to put a point source. A point source would most likely generate all kinds of modes, and then you would just calculate the radiated power if you treated your structure as an antenna, and you see how much of that power is actually leaking out. And in that case, you're not really worried about any kind of mode in the structure. It's just all the modes are going to be taken into account. Okay, so I hope that, you know, that helps, because the only filter right now for modes in what Alex has shown is the port excitation. You're exciting a port with a certain mode, and so you're looking at that kind of propagation. If you wanted to do a second mode at the port, you can also see how it responds to the second mode.
Yes, I can actually show it over here in the port definition. You can actually decide how many number of modes you can excite here. 1 mode, 2 mode, 3 modes. And so when you know the dominant modes of your structure, so you can excite as many modes as you want for the first and the second port. So when doing S12, how does the ports define? It's a wave problem. So that's exactly how the waves, how the ports are defined right here. So when you decide, first of all, when you want to apply the port boundary condition, so you choose your port from here, and you choose the face that you want to use as a port, and then over here you have the option either, if you did have 2 conductors for your port, you have the option to do the pure TM, but in this case, which is not the case here. But if you want to excite it with no number of modes, so you will just add the number of modes. Then the software will solve the eigenvalue problem here to find the mode solutions, and then it will excite the structure. I hope I have answered your question. So yes, okay, thanks, thank you. And we can also have lumped ports, by the way, where you can define the impedance, or you have your RLC parameters that you can define here when you're defining your ports. So depending on your application, you will have the option of doing different ports. And also you can define the power too, because we do have a thermal module that you can add to the software. So in case that you're actually dealing with a microwave heating structure or a high power structure like this, you can also define the power that you're applying for your structure. So Dr. Amar, if
okay,
do you have anything to add?
I think pretty much that covers the. We wanted to keep this webinar to 30 minutes, so I think we're very much on time. I just wanna, before closing. Oops, I didn't want to do that. Yeah, so I wanted to share my. Let me see. Now make myself presenter and show my screen. So I wanted to show everybody that if they want to find out more about HFWorks, they can go to our website and click on the HFWorks link. And for those who are interested in getting their hands on a trial, then you can also go to the website and click on Ready for Trial. Okay. And so with that, I would like to thank everyone for your attention, and we look forward to serving you in the near future. And if you have any questions, you can still reach us at support@emworks.com, and we'll be more than happy to answer any questions or needs you might have. You are most welcome for your thanks. Thank you, everyone, and have a great rest of the day wherever you are.
Thank you. Have a nice evening.